A camera the size of a small car, weighing more than 3 tons, sensitive enough to spot a golf ball from 15 miles away, was still being tested, not even fully operational yet, still running through the painstaking calibration process every world-class instrument goes through before its official science mission begins. And in that test data, sitting quietly among thousands of routine calibration images nobody expected to matter scientifically, was a photograph of something that had no business being there, something moving too fast, on a path too extreme, made of chemistry that doesn't match anything native to our solar system. Nobody noticed for weeks. The image simply sat in an archive, unremarkable at a glance, waiting for someone to know what they were even looking for. By the time they went looking, they realized the most powerful camera ever built had already captured proof that our solar system isn't as sealed off from the rest of the galaxy as we thought. Let's be precise from the start, because the drama shouldn't come at the expense of accuracy. Nothing about this object breaks the laws of physics. It didn't appear from nowhere, and it isn't defying any known scientific principle. What makes it extraordinary is something different and arguably more interesting. Its chemistry doesn't match anything that has ever formed inside our own solar system, and its trajectory proves, beyond any reasonable doubt, that it came from somewhere else entirely. This is the story of 3I Atlas and the camera that photographed it before anyone even knew to look. I'm your host, and this is the channel that chases down the discoveries other channels rush past. If that's what you're here for, subscribe, because there's a lot more of this coming. Let's start with the camera itself, because understanding what it's capable of is the key to understanding how this discovery happened almost by accident. The Vera C. Rubin Observatory sits atop Cerro Pachon, a mountain in northern Chile, chosen specifically for its dark skies and stable atmospheric conditions. At the heart of the observatory is the LSST Camera, LSST standing for Legacy Survey of Space and Time, and by every meaningful measure, it is the largest digital camera ever constructed. It weighs more than 3,000 kilograms, roughly the size of a small car, and its imaging sensor delivers 3,200 megapixels of resolution, equivalent to the combined output of around 260 modern smartphone cameras fired at once. Because no single silicon sensor could physically be manufactured at that scale, the camera's focal plane is instead built from 189 individual high-performance sensors, tiled together into a single enormous imaging surface. Paired with Rubin's 8 4-meter primary mirror, the system is sensitive enough, according to engineers who built it, to resolve an object as small as a golf ball from roughly 15 miles away. The entire observatory exists to serve one extraordinarily ambitious purpose: photograph the full visible southern sky, repeatedly every few nights, continuously for a full decade. That project, called the Legacy Survey of Space and Time, is designed to produce the most detailed time-lapse record of the universe ever assembled, expected to help catalog roughly 17 billion new stars and millions of previously undetected objects within our own solar system alone. Each single exposure from the LSST camera is large enough that displaying it at full resolution on a standard television would require roughly 378 separate 4K ultra-high-definition screens arranged together just to show one image in full detail. Multiply that by the thousands of exposures the camera is expected to capture every single clear night for 10 straight years, and the sheer volume of data involved becomes almost difficult to comprehend. Rubin Observatory is expected to generate more raw astronomical data in its first year of full operation than every previous ground-based optical survey combined. Processing that much information in near real time requires a dedicated global computing network capable of comparing each new image against previous observations of the same patch of sky within minutes, specifically so that anything unexpected, an asteroid on a new trajectory, a supernova flaring to life, or an object moving fast enough to suggest it doesn't belong to our solar system at all, gets flagged almost immediately rather than sitting buried in an archive for years. Combining that kind of raw imaging power with that kind of repeated wide field coverage and that kind of rapid computational triage is exactly the recipe needed to catch something rare, fast-moving, and easy to miss, which is precisely what happened before the camera had even finished being tested. Here's where the story gets genuinely strange. 3I Atlas was officially discovered and announced by the Atlas Survey, the NASA-funded asteroid tracking network the object is named after, on July 1st, 2025. But Atlas wasn't actually the first telescope on Earth to capture it. The Vera C. Rubin Observatory had already photographed 3I Atlas weeks earlier, on June 21, 2025, during its early commissioning and science verification phase, before the observatory was even fully operational and before its automated detection software was actively scanning for fast-moving objects. Nobody realized what they had at the time. It was only after Atlas made its official announcement, and the world suddenly knew exactly what to search for, that researchers went back through Rubin's earlier commissioning images and found it sitting there already, unnoticed, in data the camera had captured before it was technically ready for real scientific work. Scientists who later reviewed that early imagery reached a striking conclusion. Had Rubin's science validation survey begun just slightly sooner, it, not Atlas, might have been the observatory that first announced humanity's third confirmed visitor from beyond our solar system. So what exactly makes an object like this a stranger from outside our solar system? And why does that classification matter so much to scientists? Every comet and asteroid studied before 2017 was born right here, formed from the same original disk of gas and dust that built the planets 4.5 billion years ago. Even the ones on wildly elongated orbits stretching far past Neptune remain gravitationally bound to the Sun, permanently part of our system, looping around some orbit however long it takes. An interstellar object is categorically different. It arrives on what's called a hyperbolic trajectory, a path carrying so much extra speed that the Sun's gravity can bend its course but never capture it into orbit. It passes through exactly once, on a trajectory that proves it was never gravitationally bound to our star in the first place, and then it departs permanently, heading back out into the galaxy, never to return. Only 3 such objects have ever been confirmed in the history of astronomy. The first was Oumuamua, discovered in 2017, an oddly elongated body that displayed almost no comet-like activity, which made it a genuinely frustrating scientific mystery that's still debated today. Some researchers spent years puzzling over Oumuamua's unusual non-gravitational acceleration as it left the solar system, a subtle push beyond what gravity alone could explain, with the most widely accepted explanation ultimately settling on outgassing from volatile ices too faint to detect directly from Earth, rather than anything more exotic. The second confirmed interstellar object was Borisov, found in 2019, which behaved much more like a familiar comet, complete with a visible tail of gas and dust, and chemistry that, while somewhat unusual, still broadly resembled comets native to our own solar system. 3I Atlas, discovered in the summer of 2025, is the third, and in several important ways, the most scientifically valuable of the 3. Combining the clear cometary activity that made Borisov so useful to study with chemistry, considerably stranger and more distinct than anything Borisov ever displayed. Once astronomers knew where to look, Rubin's early test data turned out to be remarkably useful despite being captured before the observatory was fully commissioned. Using techniques developed specifically to extract reliable information from that early imagery, researchers used Rubin's observations to establish precise position measurements, gather detailed brightness data across multiple nights, refine the object's exact orbital trajectory, and study both the structure of its nucleus and the surrounding coma, the fuzzy cloud of gas and dust that develops around an active comet as solar heating begins vaporizing material from its surface. That coma detail mattered enormously because Oumuamua, the very first interstellar object ever confirmed, showed almost none of it, which is a significant part of why the first visitor remained such an unresolved puzzle for years. 3I Atlas became only the second interstellar object ever confirmed to clearly display genuine cometary activity, giving astronomers real gas and dust to study directly, rather than just a silent, inert rock tumbling silently through the dark. Rubin's orbital calculations also revealed exactly how extreme this object's path through our solar system actually is. 3I Atlas arrived on a hyperbolic orbit with an eccentricity of 14, the highest of all 3 confirmed interstellar objects found to date, and carrying roughly 58 kilometers per second of extra velocity, energy that no gravitational interaction inside our solar system could possibly account for. That kind of speed is the unmistakable signature of an object that has spent an enormous span of time drifting freely through the galaxy, unattached to any star system at all. It reached its closest approach to the Sun, called perihelion, on October 29, 2025, passing at a distance of roughly 4 astronomical units, just inside the orbit of Mars, and made its closest approach to Earth roughly 7 weeks later, on December 19, 2025, at a distance of approximately 270 million kilometers. Nearly twice the distance separating Earth from the Sun, and nowhere near close enough to pose any conceivable risk. Despite some early online speculation that the intense heat of its solar approach might break the fragile object apart entirely, 3I Atlas came through its closest pass to the Sun fully intact. While Rubin was busy mapping the object's trajectory and physical structure, other telescopes were working to decode something even more revealing, its actual chemical composition. On August 6, 2025, astronomers redirected the James Webb Space Telescope to point its near-infrared spectrograph directly at 3I Atlas, while it was still more than 3 astronomical units from the Sun. A spectrograph doesn't simply take a picture. It splits incoming light into its component wavelengths, the same way a prism separates sunlight into a visible rainbow, revealing specific chemical fingerprints embedded in that light that would otherwise remain completely invisible. What Webb found immediately stood out. The coma surrounding the object was dominated by carbon dioxide, at a ratio roughly 8 times greater than water, one of the highest such ratios ever measured in any comet studied by humanity, dramatically higher than what's considered typical at that particular distance from the Sun. Alongside the carbon dioxide, Webb also detected water, carbon monoxide, carbonyl sulfide, water ice, and fine dust distributed throughout the coma. The research team's cautious initial interpretation was that the object's nucleus may be intrinsically rich in carbon dioxide, potentially because whatever environment its ices originally formed in exposed them to considerably more radiation than the ices that built comets native to our own solar system. Then, after the comet swung past the Sun and began heading back out toward interstellar space in December of 2025, Webb took a second, more detailed look. Freshly warmed from its closest solar approach, the comet's ancient ice had converted into an even brighter, more chemically active coma, ideal conditions for a deeper analysis. This follow-up observation revealed something new: methane, methanol, and ethane, along with measurable isotope ratios of carbon and hydrogen, including deuterium, the heavier form of hydrogen, carrying an extra neutron in its nucleus. That detail is the single most important piece of this entire story, because isotope ratios function as a kind of chemical fingerprint, directly tied to the specific environment an object originally formed in. Every comet native to our own solar system carries isotope signatures shaped by the particular conditions of the young solar nebula that built the planets 4.5 billion years ago. When researchers examined 3I Atlas's isotope ratios, the results simply didn't match. A study published on June 22, 2026 in the journal Nature described carbon and deuterium ratios that are not found in any known comet formed inside our own solar system. Working backward from that chemistry, scientists attempted to reconstruct the kind of environment this object must have originally formed in, and the implications surprised even the researchers running the analysis. A separate complementary study using the European Southern Observatory's Very Large Telescope examined the object's carbon and nitrogen isotope ratios through the chemical signature of cyanide gas, adding an independent layer of evidence pointing toward the same unusual conclusion. Some of the analysis built around these combined findings suggests 3I Atlas may have originated from the galaxy's thick disk, an ancient, slowly rotating population of stars believed to have formed billions of years before our own Sun. If that interpretation holds up under further scrutiny, this object's ices could have started forming in a completely different region of the galaxy, under completely different physical conditions, potentially before our own Sun had even ignited. An object that briefly passed through our solar system in late 2025 that may genuinely be older than the star we orbit. To understand why a thick disk origin is such a significant claim, it helps to understand what that actually means. Our galaxy has a flattened structure most people picture when they think of the Milky Way, called the thin disk, where our own Sun and most nearby stars reside, formed progressively over the last several billion years from increasingly enriched gas and dust. But wrapped around and above that flattened structure sits an older, puffier, more slowly rotating population of stars called the thick disk, believed to have formed earlier in the galaxy's history, potentially predating the Sun by several billion years. An object built from material in that older population wouldn't just be old in some abstract sense. It would carry a genuinely different chemical starting point than anything that ever had the opportunity to become part of our own solar system, shaped by whatever mixture of elements existed in the galaxy at a much earlier point in cosmic history. That's precisely what makes 3I Atlas's isotope signatures so significant to researchers. They're not simply unusual readings. They represent a plausible chemical window into conditions that may have existed in the galaxy before our own Sun was even born. This is exactly why space agencies have already committed to building dedicated tools for exactly this kind of encounter. The European Space Agency's Comet Interceptor mission, currently scheduled to launch before the end of this decade, is being designed specifically around the lesson 3I Atlas taught scientists the hard way. Interstellar objects give almost no advance warning before they arrive, and by the time ground-based telescopes spot one, there's rarely enough time to launch a dedicated spacecraft to study it up close. Comet Interceptor's solution is to launch early and simply wait. The spacecraft will park itself at a stable point in space, fully fueled and ready, until a suitable target, ideally a genuinely pristine comet, or with some good fortune, a future interstellar visitor, is spotted on an incoming trajectory. Only then will it commit to a course and fly out to meet it directly, potentially giving scientists their first ever close-up spacecraft encounter with material from another star system, rather than studying it exclusively from a distance through a telescope's optics, the way every observation of 3I Atlas has necessarily been conducted so far. Put all of that together, and here's what this discovery actually represents: Not a violation of physics, not something that literally shouldn't exist in any scientific sense, something rarer and considerably more valuable. Physical, chemical proof that material from other star systems, potentially from eras of the galaxy's history far older than our own solar system, genuinely does drift through the space around us and occasionally passes directly through our neighborhood. We've now confirmed this happens repeatedly. Oumuamua in 2017, Borisov in 2019, 3i Atlas in 2025, caught in the earliest test images of a camera that wasn't even fully turned on yet. And that last detail carries real significance for what comes next. If Rubin's still uncalibrated commissioning data, captured purely as a testing exercise, could accidentally record something this scientifically important, the discoveries waiting, once the observatory reaches full operational capacity, are likely to be considerably more frequent. Rubin's complete 10-year survey is specifically designed to catch fast-moving, easily missed objects like this one far earlier and far more reliably than any previous system ever could. Astronomers involved in studying 3i Atlas have already said as much publicly. This newest, most powerful survey telescope in the world is expected to detect many more interstellar visitors once its full observing program is genuinely underway, transforming what has historically been an extraordinarily rare occurrence into something closer to a routine expected discovery. Some estimates from researchers involved in planning Rubin's survey suggest the observatory could eventually detect several new interstellar objects every single year once fully operational, a dramatic shift from a field that, before 2025, had confirmed exactly 2 such objects across nearly a decade of searching. That shift matters beyond simple statistics. Every additional interstellar object gives scientists another independent data point for understanding what kinds of material actually drift between star systems, and how common objects like 3i Atlas really are across the galaxy as a whole. Right now, with a sample size of only 3 confirmed objects, it's genuinely difficult to know whether 3i Atlas's unusual carbon dioxide-rich chemistry represents something rare or something far more typical of interstellar wanderers than anyone previously suspected. A larger sample, gathered consistently over Rubin's full 10-year survey, is exactly what would be needed to answer that question with any real statistical confidence. 3i Atlas is already leaving. By the time you're watching this, it's further away than it was yesterday, moving faster and faster back out into the interstellar dark. It originally came from never to return. It won't be back. But it left something behind that no telescope had ever captured with this much clarity before. Real, physical evidence of what another star system's leftover building blocks actually look like. Chemically, up close. Caught, almost accidentally, by a camera the size of a small car that wasn't even finished being tested yet. If this is the kind of story you come here for, subscribe and turn on notifications, because there's a lot more of the universe passing through our neighborhood than most people realize. Drop a comment telling me which detail in this story surprised you the most, and share this with someone who needs to know that the largest camera ever built caught proof of a visitor from another star system before it had even officially opened its eyes.